Now we're going to look at some applications of finding these extrema, the maximums and the minimums, or maxima and minima. And so we're going to look at some, basically what translates to story problems and talk about optimization. Now, for probably the first minute or so of the problem, it sounds a little bit like you're going back to related rates, because you have to try to take a situation and put an equation to it, and then you're going to manipulate it using some calculus. But in the related rates, remember the key word is rate. And if you're taking a rate, you're taking a time derivative, and we are not talking about time derivatives here. We are talking about just derivatives of the function itself to minimize or maximize some characteristic. Okay, so if your brain starts going, wait, haven't we already done this before? No, you did rates before. This is not rates. All right, you can do this though. So it's sometimes the math is a little bit intricate, especially the algebraic aspects of it, but you can do this. Okay, you can absolutely do this. I have faith in you. All right. So let's start off with one that's very popular, and it says find the area of the largest rectangle that can fit inside a semicircle of radius r. So didn't want to draw a little line there. So what it's asking you really, and I'm really rotten at drawing anything that's circular, is you have some sort of semicircle, and it really works out better if you can situate it. Mine's not symmetric. It really works out better if you can situate it at the origin, because then instead of having offset centers to complicate your equation, you just have something of the form x squared plus y squared equals r squared. Remember, that's what happens for a circle that's at the center, and what we're looking at is just the top part of a very kind of squished circle. Okay, a little bit of literary license there, y'all. I am not an artist. Okay, so what we're going to do is we are going to try to put some sort of rectangle inside this semicircle. Okay, so let's look at it a little bit, and let's try to figure out some things that are going on. Now, what we do know is that the semicircle, there's an equation of the semicircle, x squared plus y squared equals r squared, because it didn't tell us what the r was going to be, so it wants a generic equation. But we do know that if it is r from here to here is r. It's kind of a little hard to see. R. And here at this point, we have some generic x and y. Okay. We also note that from this point to this point is some value x over some distance y up, right? So the box, half of the box's base is x, so this other side is x as well, correct? So what it's asking us about is the area. So we also know that the area of some sort of a rectangle is the base times the height, and the base is 2x across and y tall. Okay? So those are the two things we're going to try to work together. And sometimes it becomes kind of a burden to decide where you go next. But keep in mind, okay, that it's asking you for the area of the largest rectangle. So it's actually asking you to maximize the area. So if it's wanting you to maximize the area, then you keep this equation and you try to get the information that comes from the other part of the problem and sub it into here, with the intent that this section that's over here only has one variable. So you want one variable over here to make life easy. But the question, if it had said maximize the area of the circle or maximize the radius of the circle. If it had said to maximize the radius of the circle, we'd want to keep this equation, all right? But they're wanting me to maximize the area of the rectangle, so I keep the rectangle area equation to try to massage the two pieces together, okay? Now, on the right, we either want all x's or all y's, and I'll be honest with you, if I'm ever given my choice, I'd like to have it all in x's because that's what I'm comfortable taking derivatives of. Every time I see a y, I tend to revert back to implicit and go, what am I doing here? And so I just stick with x's. So there's something to be said for choosing the simplest version you can, and whatever makes you feel better, that's what you do. Okay, so I want to keep the x's and get the y's in terms of x's. So what I'm going to do is work with this equation over here and solve for y. So we would have y squared equals r squared minus x squared. So y is plus or minus the square root of r squared minus x squared. And no, the square root does not cancel out those squares because it's a binomial underneath there. Okay? And since we want the top part of the semicircle because we chose that to make life easier, it looks like this. Okay? Now, we haven't really talked about this yet, but this is a good place to stop and talk for just a second. If you have a domain that is restricted, go way back to when we first started talking about closed intervals, and we started talking at the very beginning of the graph section, and we talked about if you have some sort of a polynomial that wanders around like this, right, then you know from algebra class that there's no absolute maximum because this goes on forever to infinity, this goes down to negative infinity. But if we close it, because that's an open interval because it goes on forever. But if we look at only a section of it, like this section, we are guaranteed that a max or min is either at an endpoint or in between somewhere, right? All we have to have is a closed interval. If you have an open interval, you know, negative infinity to infinity, then type situation, then you're not guaranteed that it's actually going to be a maximum or minimum in there to meet the goal of your stated problem, which says to find a max or a min. So this is closed, you can tell, because if you look here at this part, well, first off, you can look at the graph and tell it's closed. X is bound in between the R, right? So if you look here, X has to be bigger than 0 if you're going to have a rectangle at all, and then it has to be less than or equal to R. You know, you could squeak it on out to R, but then you would have a flat line, right? If you made X extend out to R out here, you'd have a flat line. So you don't really want to be equal to R. That would just be like a flat line. If you had it equal to 0, but this is closed, okay, because we are physically closed in here. And if you look over here, then I would want r squared minus x squared to be positive so I could have real square roots, right? So x can't be bigger than r because then I would have negative numbers. Okay, so yes, this is a closed interval, so there's a extrema in there somewhere. Okay, now, so that being said, okay, back to trying to solve the problem. So what I'm going to do is to take this y and sub it in over here. So I would have the area equals 2x square root of r squared minus x squared. Now, some people may look at this and go, but you still have two variables because now you've got x squared, but you've still got r squared. But keep in mind that r is just a placekeeper for a specific value of r that somebody would give you. So this is going to be a formula for any given r, where r might be 3, or r might be 2, or r might be 47. So r is going to be some number that is fit for whatever use you're trying to design this for. So r is just a placekeeper for a number. All right, now, so this is my one variable area equation. And now we're going to take the derivative. So the derivative with respect to x, right? You would have your 2, and this is a product. So it's the first times the derivative of the second, which, remember, this is r squared minus x squared to the 1/2, right? That's what you're taking the derivative of. So you'd bring the 1/2 down, leave the inside alone, take 1 off the power, loop back in and take the derivative of the inside. Now remember, when you're inside, the r squared is just a number. You just don't know what it is. Okay, so the derivative of a number squared is still 0. Plus, and then it'd be the second times the derivative of the first. So far, so good? All right. So this is 2. Now, this 1/2 and this 2 cancel each other out, right? And this x and this x can be combined. So you'd have minus x squared times r squared minus x squared to the negative 1/2 plus r squared minus x squared to the positive 1/2. And we can factor out this common r squared minus x squared. And the smallest exponent for that is negative 1/2. So we're going to factor that out, and that would leave me negative x squared from the first term. And what does this have to be right here to get a positive 1/2 after you multiply these two together? Remember, you add the exponents. And what do you add negative 1/2 to be able to say you get the positive 1/2 back? This would have to be a 1. So this value right here is 1. And an understood power of 1 is just itself. Okay, excuse me. So you would have 2 r squared minus x squared to the negative 1/2. And you can clean up in here a little bit. And this would be negative 2x squared plus r squared. And this would look something like this. This is in terms of x. So I guess we really should put x up here. I don't know if your teacher's picky about that or not. I should do that. Now, this is the derivative, and remember when we were looking at where you have a maximum or minimum, you look at where the derivative is equal to 0. I don't care where it's undefined, okay? I want to know where the derivative is equal to 0 because I'm not graphing this, okay? I just want to find a value, so I need to find out where the numerator is equal to 0. So if you want 0, you get it from the numerator. If you have 0 on the bottom, it's not a 0, it's undefined. Okay, so the question of the day is, where is the numerator equal to 0? And this 2, well, let me write it down anyway. Okay, it's not going to affect what's 0, so all I really need to look at is this interior portion. And so we would have r squared is equal to, let's solve it for x squared. So x squared is equal to r squared over 2. So x is plus or minus r over the square root of 2. And we don't want a negative r, okay, so we would want the positive version over the square root of 2. Now, here we go. I want the area. I don't necessarily, now if they asked you, right, for the dimensions of the box, that would be another thing. This would help you with the dimensions, because remember the box or this rectangle was 2x by y, right? But they didn't ask for that. They asked for the area, right? So we had an area equation that looked like this, which was way up there, right? And so we can substitute this in and say this is 2 and x is r over the square root of 2 times the square root of r squared minus another x, which is r over the square root of 2 squared. So this is 2 r over the square root of 2 times the square root of r squared minus r squared over 2, because this square affects the numerator and the denominator. So here we go. So you have 2r over the square root of 2. Now what we're trying to do is to clean up what's going on inside. So I would need a common denominator of 2. So this would be 2r squared minus over 2 minus r squared over 2, right? And when you clean that up, you would have the square root of 2r squared minus 1r squared is r squared over 2. I'm doing this really slow because sometimes people just race through all this algebra, and it's algebra that's killing students to get this cleaned up. So I'm trying to do this really slow. If this is boring, you just fast forward through all of these parts. And so the square root of r squared is r, and the square root of 2 is the square root of 2. So you have 2r squared over 2. So it's r squared. So when it says find the area of the largest rectangle that can fit inside of a semicircle, well, if I tell you what r is, the area is whatever r squared is, and that's kind of cool. You know that it's totally based on r squared. I mean, I can kind of get that. Okay, now let's go over here. Let's do another one. See if I can get all the way up to the top. Here you go. All right. So let's say you have an art project and you want to form a circle and a square from 8 feet of wire. And how much of the 8 feet should you dedicate to the square and to the circle if you want to max the area of each thing? Okay, so what you've got is you're making some sort of a square, which would be, let's say, x by x, because that's what squares do. And then you have some sort of a circle, and this would be based on r, right? So the total area would be the area of the square plus the area of the circle. Okay, now the 8 feet of wire that you're actually going to use, you're actually going to take the wire and form it, into a square, and it's going to form into a circle. So if you think about the actual mechanics of trying to form these shapes, the 8 feet are going to form the perimeter or the circumference of the circle, the perimeter of the square, the outside, and then the circumference of the circle. So that 8 feet is going to form the perimeter. Sometimes these relations are a little hard to visualize. If you can just sort of put yourself in the problem and think about trying to do these things that they ask you for, sometimes it helps a little bit to kind of figure out what you're doing and saying, because that's part of the process. So the perimeter for a square is 4 times the length of one side, and the circumference for a circle is 2 pi r. And have you ever noticed that the circumference for a circle is the derivative of the area? I've just always been fascinated with that. Totally off the point. Okay. And you only have 8 feet. Okay. Now you've got, let's call this equation 1, and you've got this as equation 2. and you need to work them together, kind of interweave them in together. So which one is the one you're going to hold on to, and which is the one you're going to fold into it? Well, that depends on what they ask you. Okay, so this says they want to maximize the area. So since the question is to maximize the area, then you have to take the derivative of the area function. So you want to keep that one. That means you're going to have to fold the information that comes from the perimeter into that. Okay, so this is the one we want to keep. And then we're going to try to utilize this equation to the perimeter one. Now, what I have is an area in terms of x and r, and I'd really like to have it be only one variable. So I would like to do away with the r and just substitute in x's. So let's see what we can do. So 8 minus 4x is equal to 2 pi r. So r is 8 minus 4x over 2 pi. So r is 4 minus 2x over pi. Would you go for that? Okay, and we're going to substitute this in there. So I would have a is x squared plus pi, and r is going to be 4 minus 2x over pi squared. Sometimes you do all this difficult work and then forget something like the square, and then life is just difficult. Now at this point, you could call this a of x because now it's all in terms of x. Before it was not. I'm not going to be picky, so let's just stick with a. All right. Now, so this is a, and my job is to try to figure out where this might be equal to 0 and find out a maximum. You can clean it up a little bit now and then take the derivative, or you can try to take the derivative and then clean it up. Let's try to practice manipulating our algebra and then take the derivative. Okay, so we would have, if you want to do it the other way around, we should end up at the same spot. So you'd have pi, right? Now there's a 2 in common up here. Squared. Okay, so far? So this is x squared plus, now this square applies to the 2 and to this part. So that 2 is actually a 4. So you have pi times 4 times 2 minus x. Somehow my x's have become pi's. Okay. I think they just look like that. X squared. There we go. All right. So that's 4, and you have 2 minus x squared over, and the square applies to the denominator, pi squared. So you have x squared plus, and the pi's cancel, 4, or one of them cancels, 2 minus x squared over pi. So you need a common denominator. Over pi. So this turns out to be pi x squared plus 16 minus 16x plus 4x squared over pi. Now you could, take the derivative here, but let's just keep going. So, because I want to show you this. So do you see how you have 2x squareds right there? So this would be 4 plus pi x squared minus 16x plus 16 over pi. So when you take the derivative of this, because we haven't done that yet, okay, you can bring out this coefficient, the 1 over the pi, and then you would take the derivative of just this right here. So you would bring down the 2. You would also have your 4 plus pi, leave the x alone, take 1 off, loop back in, it'd be a 1. Okay, minus 16. And what you want to do is find out where this is equal to 0. Well, 1 over pi is not going to help you get to 0. So 2 times 4 plus pi x minus 16 could be 0. All right. And when you solve this, and you'd have to use your calculator, it turns out to be give or take about 1.12 feet. Okay. Now, what we really haven't talked about is let's when we're doing all of this, right? What we had is a square and a circle, right? Now, there is not, this is not like it's going off to infinity or anything else like that, right? Because you only have 8 feet to deal with. So what you can do is, let's look at kind of like the endpoints, okay? If you take the 8 feet and put it only on the square, then you would be 2, right? All the way around, okay? And that, because these are all x's, right? So we're looking at what's going on with the square because this doesn't have r in it. So the biggest x can be is 2, because that would take up all the wire and you would have no circle at all, okay? Or you could make x be 0. And if x was 0, then you would not have a square at all and you would have only a circle. So if x is 2, you have only a square. Okay, if x is 0, you have only a circle. Okay, and if x is 1.12, then you have both a square and a circle. Now, let's talk about what the area would be for each one. If you talk about when x is 0, okay, so remember when x is 0, you have only a circle because that says you're not putting any of the wire into the square. So if you substitute that back into your area formula, and remember your area formula was x squared plus pi 4 minus 2x over pi squared, okay? So if you substitute 0 into that, you get 5.09 square feet, okay? If you substitute the 1.12 in there, you get 2.24 square feet. And if you substitute the 2 feet in there, remember this, when x is 2, you have only the square. Okay, this is both. You get 4 square feet. Okay, so now let's talk about this for just a second. If you are an artist or you're designing this, even if you're not an artist, you have this vision, okay, and it is your priority to have both a square and a circle. This is the one you're going to pick, but notice that it's not your best overall area, okay, between the two. If your priority is that you're going to try to frame something and you thought, a square and a circle might be nice, but then after you found this out, you're going, okay, I think I can make everything fit inside this circle, then you may want to pick this one. Okay? So, but if your intent was you have to have a square and you have to have a circle, then this is the combination that you're going to pick. Does it make sense? Okay. All right. Way back up here. All right. This is also a very common problem, and this has to do with designing like a can, okay? So Says you work for Acme Food Company and you've been asked to design a cylindrical can to contain 170 cubic inches of vegetables at a minimum cost. So you are trying to minimize the cost. And in order to minimize the cost, you need to minimize the surface area. That's been your task assigned. What will be the dimensions of the can? All right. Now, so I want to minimize the cost by minimizing the surface area. So you have some sort of a can. Okay, that's a pretty bad can. All right, so there you go. Now, the the controlling kind of objective function here is you have a volume of 170 cubic inches, and the volume that it holds is independent of whether you actually have a bottom or a top on it. So it's pi r squared h. Okay? The surface area, and let's just call it, can we call it A for surface area? Is due to the sides, which is 2 pi r, which is the circumference, stacked h tall. And then you have a, a solid disk on the bottom and a solid disk on the top. So, because you'd have a top and you'd have a bottom. So this is 2 of the pi r squared. Okay? Now, if you want to minimize the surface area, this is the one you're going to keep. And you're going to try to figure out how to get it in terms of one variable so you can take the derivative, right? Now, so this is 170 equals pi r squared h. And given my preferences as to do I really want to work with h or do I want to work with r, I probably want to work with r. So I'm going to solve this first equation for h. So h is 170 over pi r squared, and I'm going to substitute it in over here. So now right at the moment, A is in terms of R and H. I'm getting ready to change it into R. So if you want to go A of R, that's fine. I'm just going to do A. Some of your teachers, some books just do A. Some books do A of R. Some teachers do A. Some teachers do A of R. You need to kind of get familiar with what your teacher wants. So 2 pi R and H is 170 over pi R squared plus 2 pi R squared. So cleaning this up just a bit, you get 340 over r plus 2 pi r squared. And this is actually 340 r to the minus 1. Some people can take the derivative of it while it's still underneath, and some people can't, so I'm going to show you that. So what we're going to do is to take the derivative now, and it'll be minus 340, because you bring the power down, leave the inside alone, right? Take 1 off the power, and this would be 4 pi r. So this is negative 340 over r squared plus 4 pi r. And what we want to do is to figure out where this is equal to 0. So 4 pi, I lost somebody along the way here. 4 pi r, yeah, I left out a step on y'all. I'm so sorry. Let's go back up here for a second. Yeah, we're okay. Okay, well, I guess I can just do it here. So to clear out this r squared, you'd have 0 is equal to negative 340 plus 4 pi r cubed. So r cubed is 340 over 4 pi. So r is the cubed root So when you run this on your calculator, you get 3.00208, which is close enough to 3. Now, one of the things that you can do at this point is somewhere in here you might want to consider if this is a closed interval problem and has endpoints, kind of like how big can x be and how small can x be, and or if it's one of these, like for instance, let's go back up here to your little can, right? You could keep making r, because the volume is dependent on r. You could keep making r go to infinity, right? It's there is a limitation, but you could keep making it get bigger and bigger and bigger and bigger and bigger. But h is going to shrink and shrink and shrink and shrink and shrink. And so if you're going to have a can, it's technically got to have some height to it, because if you make r go all the way out as far as it can, you just have kind of you just have the cap, it's just the bottom really, I guess. And so if you think about it, as r goes to infinity, okay, then a goes to infinity because of this r squared. Now, granted, this is not kind of true that you have absolutely no limits on it, because you have to go buy the materials and it still has to make a can. But theoretically, according to math, and as r goes to 0, a goes to infinity because of the 1 over r. Okay, and if you have some sort of a function, and as you get farther out this way, it's going to infinity, and as you get closer to here, it's going to infinity, then there has to be some sort of a minimum in there. So you could do it that way, or you could sit here and go, all right, it's actually 3.002, but let's just stick to this. And you'd pick a number to the left and a number to the right, okay? And if r is 4, then the derivative, when you run this into a prime is equal to minus 340 over r squared plus 4 pi r. Okay, before I multiply both sides, this part right here. Okay, then a prime turns out to be negative 59.86. Okay, and if r is 2, and if r is 4, then a prime turns out to be 29.015. So it goes from negative to positive, and this would be decreasing, this would be increasing. So see your little minimum right here. All right, so that's another way to look at it. So r is 3, right? And we know that the volume is pi r squared h, and we know that we wanted 170, and this is pi 3 squared h. So h is 170 over 9 pi, which turns out to be 6.0125. So 6. So we're going to say 3 by 6. Okay? All right. One more. And I'm going to take this over here. And it says find the point on the curve y is equal to 1/2 x squared that is nearest to 4, 1. So 1/2 x squared looks like this. It's a parabola, right? Well, it looks better than that, but okay. It looks kind of like this. All right. And we're trying to figure out, so 1, 2, 3, 4, 1 would be like right here, 4, 1. Now the question actually should be, is the parabola above 4, 1 or below 4, 1? I think you could probably guess it's above, but let's just say, so up here, when x is 4, right, 4 squared 16, half of that is 8. So it's clearly up above. So my picture looks about right. And the question is, find the point on the curve that is nearest to 4, 1. So that doesn't necessarily mean that you're going to have it being the closest by going straight up to 4, 8. It could be any point along here. So here we go. Now, the question is find the nearest point. So that would be the shortest distance, right? The shortest distance between that point and the curve. So you're looking at the distance formula. And if you remember this from algebra class, it's x2 minus x1 squared plus y2 minus y1 squared. Okay? And you have your point 4, 1. So this one doesn't really seem to have two formulae that I'm trying to insert or intermingle. It does have a piece of information though. So the distance is the square root of the x on my curve minus 4 squared plus the y on my curve minus 1 squared. All right. And we also know that y is equal to 1/2 x squared. Now there's a relationship between the two because right now I've got the distance in terms of x and in terms of y. And I really like working with x, so I'm going to leave this with y equals and substitute that in there. So the distance is equal to the square root of x minus 4 squared plus x squared. I could try to make that a little bit better. X squared over 2 minus 1 squared. Okay? Now, you can take the derivative of this, or I have seen similar problems like this where they have a suggestion where you square both sides, which you're legally entitled to do. And if you have a teacher who's done this, they may have squared both sides, and then they take the derivative of both sides. Okay, but here's the problem. Okay, for me. Okay, this is a problem for me. May not be a problem for your teacher, but it is a problem for me. Okay, in the fact that I'm always looking at it going, am I comfortable enough with this alternative situation to want to work harder? Or would I rather be with the other situation and not deal with this? Because what you're taking is the derivative with respect to x on both sides, because you have x over here, right? So in order to not go insane, let's call this r, okay, for like Pythagorean's theorem for just a second. So we just had x. We don't want to call it x and y again. And when you take the derivative with respect to x on the left over here, you would bring the power down, leave the inside alone, take 1 off the power, loop back in, and take the derivative with respect to x. So you're looking at implicit, okay? And then you would take the derivative of the other side with respect to x, and then you would have to take this 2r and divide it out over here. And it works. Okay, I actually went through and checked it because I had seen other approaches like this, and I thought, and it does work. Okay, but I'm like, no, I'll work with the square root. Okay. So if you like this idea about the implicit, go for it. And if you don't like the idea about the implicit, you ought to try it at least once so that you can see that it is the same. Okay, but I'm comfortable over here with the little square root guy. All right. So if you want to go back and let's call it d for a second, because I didn't want over here go, this is dx. It's just too weird. Okay, so, all right. So here we go, d. You have to laugh. Okay, really, you have to laugh sometime in here. So d prime is, and this is d of x, but I'm just going to call it d prime. Bring the power down, right? Leave the inside alone. Take 1 off the power. Loop back in. So you bring the 2, x minus 4, take 1 off the power, loop back in, derivative is 1. plus, bring the 2 down, leave the inside alone, loop back in. And when you take the derivative of x squared over 2, right, you'd bring the power down, right? And it's going to cancel. So what you have is just an x here, right? Now, when you do this, okay, so now let's think. This 1/2 is going to be in the denominator, right? When you clean this up. This, because of the negative 1/2 power, is going to be in the denominator, right? Because of the negative. This stuff, whatever that is going to be in the numerator. And when you're on a time test, every time you can do something that shaves a few seconds there and a few seconds over here and everything, just makes life a little bit easier at the end. So if I'm looking for where this is equal to 0, the only place I'm going to get 0 is from the numerator. So where is 2 times x minus 4 plus 2x times x squared over 2 minus 1, because I combined these two? Equal to 0. Okay? So you'd have 2x minus 8 plus x cubed minus 2x is equal to 0. So these cancel. So x cubed is equal to 8. So x is equal to 2. And if you go over here and use 2 and you check to the left and the right, this is going to be negative and this is going to be positive. Because look, what you're checking it into is x, well, no. Yeah, let's talk about this for just a second. If this 1/2 is down at the bottom, it's going to be positive, right? This part here that's down at the bottom and then square rooted, it's going to be positive unless you have imaginary numbers down there, which are not, okay? And then this part is going to be whatever it is, okay? So those two things are positive. So what we're looking at is what's going on with this one, okay? Because what you've got is whatever's going on there with x cubed minus 8 over the positive 2 from the 1/2 and the positive square root, which doesn't change anything. So if you have, say 1 cubed minus 8 is negative, 1 cubed, and then 3 cubed minus 8 is, I don't know, some positive number, 27 minus 8. Okay, so it's a minimum, so x is equal to 2, and then the question was, what's the point, right? So subbing it back into y is equal to 1/2 x squared, then y is also 2, and your point is 2, 2. There you go. All right, so much for optimization. So good luck. I will see you in the next video, which actually is going to be going over everything a little bit. And then we'll move on to other stuff. And don't forget to like and subscribe. And see you at the next video.